This video is going to cover the F-test for evaluating the equality of two variances. Let's start with a discussion of why we'd want to do this. So sometimes we are interested in the variances themselves. So for example, maybe I've got two measuring devices and they're being used to measure the exact same thing. And so maybe I take independent samples of measurements. I have multiple measures of something with one device, and I have multiple measures of the same thing with another device. And I'm really interested in which of these gives a more reliable estimate. So on the average, which one comes closer to its mean. Hopefully they're both unbiased. Well, in that case, a question of reliability is really a question about variances, because variances are asking what is the typical squared distance of an observation from its mean? And so the more reliable one would have lower variance. And so maybe I want to test that. Probably the more common use of this is when you're doing an independent sample t-test for means. So I want to compare whether one mean equals another mean. Now, if you remember, the first decision that you have to make when you conduct that test on means using t-distribution is whether to assume that the variances of the two populations are the same. So if you do, then you go off and you pool your variances and you make one estimate of the variance. If you don't make that assumption, you have to estimate the variances separately and use a slightly different test statistic then. All right, so those are probably the two most common uses of this test. I'll mention that this F distribution is one of the most important distributions in all of statistics. So when you go on and take further courses, for example, in regression, or if you take a course in designed experiments, you will use the F distribution a lot. And so it's worth knowing for that reason as well. So what is an F distribution? Well, if I have two independent chi-squared random variables, then what I have, if I divide both of those chi-square random variables by their respective degrees of freedom and then compute the ratio, I get an F statistic. So what's a chi-square distribution? Well, remember we talked about chi-square distributions back when we were in the confidence interval chapter and we were looking for a confidence interval on variances. So just to refresh your memory, I summarized one of the key results that we had from that section. So a chi-squared random variable is just n minus 1 times the sample variance divided by the population variance. Now, what's the sample variance? Sample variance is, take the sum of squares, so xi minus x bar squared, add those up, and divide by n minus 1. Now, we had another name that I introduced for this. I called this the total sums of squares. And so you could rewrite this as the total sums of squares over sigma squared as well. So whenever we have a sum of squared normal random variables, we're going to use the chi-square distribution to model that. And so we did that in the case of finding a confidence interval for variances. Well, we're going to take this a step further now in that we don't have just one chi-square distribution, we've got two, and we're computing their ratio. So I'm just going to mention one property of the chi-square distribution, not the chi-square, the F distribution. It has a range from 0 to infinity. And the reason for this range is that I have a ratio of two non-negative quantities. So I'm adding up a bunch of squared things and dividing that by the sum of a bunch of squared things. That sum of squares can never be negative. Therefore, if all my xi's equaled the mean, x bar, then it would be 0, and in which case f would be 0, but this thing can never be negative. So this is only a non-negative random variable. Well, let's get to the f-test for the equality of variances. These are the assumptions that we're going to make on this test and notation. So I'm going to use this notation. So let's just go over to the scratch pad. When I say x11, that's the first observation from population 1. And this is going to go all the way up through x n1, comma 1. So in my first population, I've taken n1 measures. And then in my second population, we're going to have x12 all the way through xn2, comma 2. So I have n2 observations from the second population. So anyway, I've sampled n1 observations from one normal population with mean mu1 and variance sigma 1 squared. And then I've sampled n2 random variables from an independent population. These are independent random variables. So they're independent of one another with mean mu2 and variance sigma 2 squared. I'm then going to I'll just add a subscript. So s squared sub j is going to be the sample variance from population j, where j is 1 or 2. So the following has an F distribution. So if I divide the sample variance by the population variance, that's for population 1, I do the same thing for population 2, this has an F statistic. So why is that? Well, it comes back to this definition that I gave you. So I could start adding a subscript j to everything. So let's just add a subscript j to everything. And what is an F distribution? Well, I take a chi-square, divide by the degrees of freedom. So if I divide by the degrees of freedom, that n1 minus, if I divide by the the degrees of freedom, that nj minus 1 goes away. All right, so I'm just left with the sample variance over the population variance. And so this is a chi-square, and the bottom part is also a chi-square. We can use this result to test, well, the one we most care about is whether two variances are equal to each other. We could also test whether the ratio equaled some constant if we want, but that's not done nearly as much. We can also find confidence intervals with this. So why don't we go do an example problem, and we'll see how this works. So I think a really nice problem is the candy bar problem that I think I made you do some problems off this back in week 1. Here's the situation. We make candy bars, and we draw a random sample of 20 candy bars that we produced, and then we modified the machine. We did something to it. So think of this as the pre-measures. And then we made a bunch more candy bars. We drew a random sample, and we took 20 in that random sample. Here are their weights. And so if we look at the box plots of this, what should be obvious is that it looks like we did something to destabilize the machine. Before whatever we did, we were pretty consistent. Variance looked smaller, and whatever we did to that machine destabilized it. That's what the box plots are showing us. But remember, we've got small sample sizes, and we might just be reading into sampling variation here. Maybe we had a couple observations that were a little bit more extreme than they could. So we'd like to do a formal test of this. So to do this in R, we can use the var test function. And so this gives us a test of variances. So it takes the exact same formula notation that boxplot does. And let's go through what we have here. So our alternative hypothesis is stated. It's the true ratio of variances not equal to 1. Well, let's go unpack what this means. I'm going to go back to my document camera. And let's say this: h naught sigma 1 squared is equal to sigma 2 squared. Now, what I'd like for you to notice is that this is exactly the same thing as sigma 1 squared divided by sigma 2 squared equal to 1. So when the ratio equals 1, that's the same as the variances are equal to each other. My alternative hypothesis is going to be that sigma 1 squared is not equal to sigma 2 squared, and that is completely equivalent to this ratio not equaling 1. And so when we go look at what R is saying, the true ratio of the variances not equal to 1, that's, translated into symbols, that's what R is talking about. All right. Now, whenever we test a hypothesis, we need to come up with a test statistic to measure how much our data violate the null or are inconsistent with the null. So we go back to the course packet. My F statistic was this. So let me go write it again. S1 squared over sigma 1 squared all over S2 squared over sigma 2 squared. But if I assume that the null hypothesis is true, so we condition on the null, then notice this F statistic is simply the ratio of the variances. Okay, so this is a test statistic that's going to tell me whether my data contradict the null. So if H naught is really true, then what should happen is that F should be about 1. Okay, so if my variances were really equal and I go draw two samples, then the ratio of them ought to be 1 because S1 squared is approximately S2 squared. So we could say because S1 squared is approximately equal to sigma 2 squared down to sampling variation. If H1 is true, then what's going to happen is this F does not equal 1. So if S1 is much bigger than S2, then F would be much bigger than 1, or bigger than 1 at least. On the other hand, actually it would be, right. I said that right. On the other hand, if S2 is greater than S1, then this thing is going to be close to 0. In either way, they're different from 1. So that's what we really need to evaluate. So if we go back to the course packet, I thought I would not just look at what these variances are. So let's just go compute them. I did this with a tapply command. You could also use dplyr with a group by, but the tapply makes this a little bit more convenient because I get an array with the two results. So these are the two sample variances. So I called this object S2 because this is the sample variance of the post group, pre-group sample variance of the post group. Now I'm going to go compute the ratio. I decided to call it F1. So here is the ratio, 3.344. Now that number we've seen before. So in the R output, they gave us the ratio of the variances, and that's exactly what that number is. All right. I thought I would just show us what an F distribution looks like. So remember, in R, there's 4 probability functions. The D gives us the density, P gives us the CDF, and then Q gives us the quartiles, R would give us the random variables from that distribution. So I made myself a sequence of x's from 0 to 4, and I'm going to plot the density. And so you can see that the F distribution is fairly right skewed, and it can't be less than 0. Now I'm just going to put what my F statistic would be if the hypothesis, the null hypothesis, were perfectly true. So if it were perfectly true, the ratio of these variances would be exactly 1. And what I want to know is, to what extent does my test statistic contradict that? So this was my test statistic. And so what I really care about is, what is the area in this tail? So from 0.344 down to 0, what is the area in that tail? And so if the area in that tail is large, then I would say there's nothing wrong with the null hypothesis. Alternatively, when the area in that tail is very small, then that's contradicting this assumption that we made, that the ratio of the variances equal 1. Okay, so small tail probabilities mean one isn't very plausible. Large tail probabilities mean that they're highly plausible. All right, so we can go find the area in that tail with the PDF. So the area in this tail is 0.0124. Now, if I have a two-tailed test, I have to multiply that by 2. So my p-value is 0.0248. So let me just go write that down before I forget it. So p is 0.0248. That's less than 5% if we're going to use that cutoff. So we're going to reject H0. So, I'm going to come back up here and just cross that out. That's not very plausible given the evidence that I have at hand. Now, you might be wondering, what would have happened if I'd taken the other ratio variances? So what would happen if I divide S2 by S1? And the answer is, well, you'd get a number like 2.9 something or other. I'll go add that. So an alternative way would be for me to find the area in this tail. If the area in that tail is small, that means that the assumption that I've made that the variances are equal is not very plausible, and I'm going to reject it. Alternatively, if the area in this tail is quite big, I'm not going to be able to reject H0. So let's go find the area in that tail, and we hope that we're getting exactly the same thing. So I'm going to take 1 minus, so remember this is a cumulative distribution function. I want the area in the right tail, so we do 1 minus. And so notice that is exactly the same as what we had in the area of the left tail. This is not a symmetrical distribution, so you have to find them separately. What did we get when we did our F-test earlier? Well, we had a p-value up here, which was minus 0.02841, and that is exactly what you get when you take 2 times the tail of probability of 1 tail. All right, so that's a lot of explanation, but what you would do in real life is you would run this F-test after you look at your box plots to make sure that the populations are roughly normal. To some extent, maybe you're interested in the ratio, but you're probably going to go straight to the p-value. You'd say, well, that p-value is less than 5%. Therefore, I'm going to reject the null hypothesis and go with this alternative that the ratio of the variances does not equal 1. In other words, they're not equal. Okay, one last thing. There's a 95% confidence interval. Where does that come from? So I gave the formula here, but let's try to derive this. And so I'm going to go over to the document camera again, and we're going to do the same thing that we always do with confidence intervals. I'm going to write down a true statement. So let's just take 95%, and that's equal to the probability that if I'm going to use this notation, 0.025, that's going to be the 2.5 percentile from an F distribution with our degrees of freedom. And then I'm going to go write the ratio the other way. So S2 squared over sigma 2 squared divided by S1 squared divided by sigma 1 squared. That also has an F distribution. And I'm going to go write out the 97.5 percentile. Now, I can do a little bit of math on this. This is exactly equal to, I'm going to multiply both sides, all three sides of this, by S1 squared over S2 squared. So S1 squared over S2 squared times this percentile is less than, well, these were both in the denominator, and so they're going to flip around to the numerator, and we end up with this ratio of variances. And then on the right-hand side, we have the exact same thing, S1 squared over S2 squared multiplied by a different percentile, but the product is the same. All right, and so what this says is if we just take the ratio of the variances, multiply it by the percentile, we should get the upper and lower bounds of my confidence interval. So let's go back to R, and let's just see if this works out the way I think it will. So how do you find a quantile of an F distribution? Well, you use QF, and you'd give it the percentile. So let's say 0.025. We had 20 observations in both cases, so let's give it 19 and 19 degrees of freedom. So this value, 0.39 something or other, would be the point where there is 2.5% in the tail. Let's just add that to the plot to see where it is. And I'll make it in red so that we can distinguish it. And so notice our test statistic is actually beyond that cutoff. So what that means is we're going to reject this null hypothesis. But, all right. So let's actually go find the confidence interval. So what I just told you was take the ratio. So that was just the test statistic I was using in my F test and multiply it by the percentile. So here we go. And let's do the same thing for the upper bound. And what I'd like for you to notice is that this is exactly equal to what we got when we did the VAR test. So let's just go, let me just convince you of that. The lower end is 0.136, the upper end is 0.869. So the interpretation here is that we think the true ratio of variances, so if we take the pre-measures, the variance of the pre-measures, and divide by the variance of the post-measures, the true ratio that we just computed is somewhere in that window. Now, what's really important to notice is that the value 1, the reference value for our hypothesis, is not contained in there. So let me just go over to the document camera and write that down. So note, the value 1 is not in that interval, and I can't remember what it was, 0.136 to 0.869. So I just wrote that in here. So we would reject the possibility that sigma 1 squared divided by sigma 2 squared is equal to 1. So that reference value is not contained in the confidence interval, and therefore we rule it out. All right, so that's it for our F test.